Hello again, I hope everybody is doing well. We have another short video today talking about rational functions. This is just an introduction of some of their basic properties. But what I like to call them, instead of just plainly rational functions, is I think it's a lot more clear to call them rational functions of polynomials. Because you can have a function which is represented as a ratio of other functions. They don't necessarily need to be polynomials. So it's just a nice little clarification to point out that we are only using polynomials as the pieces. So we're going to have any function of the form r of x is p of x over q of x. Now p and q are going to be polynomials. And we have a little bit of a restriction because we can't divide by 0. That's bad. We also say that q of x is not equal to 0. Specifically, we're saying that it's not the 0 polynomial, but in general, we also don't want q of x to be equal to 0 because bad things happen when you divide by 0. Now, rational functions, like polynomials, count as nice. They have a little bit more problems because we can divide by 0. We want to avoid those. But generally speaking, the domain of any rational function is any value of x for which you do not divide by 0. So let's pick a simple rational function to look at. If I say r of x is equal to 1 over x, this is kind of our basic example. I have to say here that x is not allowed to be equal to 0. My top polynomial here is just a constant function 1, and my bottom polynomial is simple linear function x. But we can see with this easy example here is I can plug in any number and get a result as long as the number I plug in is not 0. So I'd say the domain, that's interesting. Domain is minus infinity up to 0. We can't include it, and we just skip it. We go to 0 up to infinity. Now, one of the unique properties of rational functions is discussion of asymptotes. But before we want to talk about asymptotes, we want to talk about simplification. So consider this rational function. I've got x squared minus 1 over x plus 1. Now, you might recognize the top as being factorable from our previous video. This guy can rewrite this as x plus 1 times x minus 1 all over x plus 1. Now, it's tempting to look at these parts here and try to cancel them, but we're actually not allowed to do that when they're equal to 0. So this is not equal to x minus 1. What I can say is that it is equal to x minus 1 if x is not equal to minus 1. And the reason for that is if I let x be equal to minus 1 in the original representation of my function, then I'm going to have the result 0 divided by 0, which is undefined. So I can't include that in my domain. But every other value of x will work just fine. Now we have two fundamental versions of asymptotes. There's actually an additional type, but it's just a generalization of one of the others. So 1 we can have vertical. And these are fairly easy to spot because they always come from division by 0. So in my first example, when I used 1 over x, I see on the bottom here that x cannot be equal to 0, because if I let x be equal to 0, I'm going to have division by 0, which is bad. But when I have division by 0, that means I have a vertical asymptote when I graph it at x equal to 0. But we have some caution here. Vertical asymptotes can be deleted. So generally speaking, actually, I don't have to do generally speaking. I have an example right up here. If I'm using r of x equal to x squared minus 1 over x plus 1, I look down here and I see that x cannot be equal to minus 1. It's an easy spot. So I could say that I have a vertical asymptote at x equal to minus 1. But up here, we see that I could have canceled x plus 1 on top of and on the bottom as long as I was looking at x values which are not minus 1. So what this says is that everywhere except x equal to minus 1, r of x is equal to the line x minus 1. At x minus 1, I have a vertical asymptote, but it kind of got deleted, and instead this is going to be a hole. So as a rule here, a factor that cancels with the bottom so if I have a factor on top that cancels with a possible vertical asymptote, then what's going to happen is I get a hole. And we'll go over each of these cases in the next section when we're actually talking about graphing these rational functions. But right now we're just concerned with what do we have to look forward to. Vertical asymptotes you're always going to find on the bottom of the fraction, but you should always check them against the top of the fraction for the factors to see if you have a vertical asymptote or you actually have a hole. Our second type of asymptote is the horizontal asymptote. And these, in terms of calculus, are represented by limits. Generally speaking, an asymptote is a tendency of a function for extreme values. So vertical asymptotes, they count for extreme values of y. Horizontal asymptotes are going to count for extreme values of x. If I'm looking for a horizontal asymptote, then I'm looking for a line that my function will approach as I let x become extremely large positive or extremely large negative. But we're not doing calculus right now, so we're not actually going to do limits. But all the work with limits that we do in calculus boils down to a simple test. We'll have r of x equal to p of x over q of x. And what we do is we look at the degrees. If the degree of p of x is less than degree of q of x, What this basically means is that for extreme values of x, p of x is going to be smaller. And as a result, my horizontal asymptote will always be 0. On the other hand, if I flip the inequality, if the degree on top is greater than the degree of the bottom, then I have no horizontal asymptote. What I actually get in this case is we get a slant or oblique asymptote. Or maybe something a little bit more exotic. The point is, the asymptote is not going to be a horizontal line. Usually what happens in these cases is my rational function blows up towards infinity or minus infinity in either of the two directions. Speaking in terms of general functions, you can have a different horizontal asymptote for positive side and negative side, but when we're dealing with polynomials, they always match on the left and on the right. So we don't have to worry about those troublesome cases in this class. Now the case that we're missing is if they are equal. So otherwise, if the degree of p of x is equal to the degree of q of x, then we will look at the coefficients of the highest degree terms. And this one's best done with an example. So let's say I have r of x equal to, we'll say 3x squared minus 4x divided by 5x squared. Let's make it a minus 5x squared plus 2. So I've got degree 2 polynomial on top and a degree 2 polynomial on the bottom. Now what this rule says is I take the coefficients of the highest degree terms on the top and on the bottom. So my horizontal asymptote, we just take the numbers, is literally y equals 3 over minus 5. It's like I take the first numbers I see when I write them out and I just ignore everything else. Now our last type of asymptote is the slant or oblique. And how we find those is actually polynomial long division. So these occur when you have no horizontal asymptote, and from the previous page we saw that that means the degree on the top is bigger than the degree on the bottom. So when that happens, let's say we've got x squared plus 2 divided by x minus 1. I specifically chose this so that it does not factor and cancel easily. But what I do is I do polynomial long division. So I'll change this into a division format. I'm looking at x squared plus 0x plus 2, and I'm dividing x minus 1. I need x to make x squared. So we have minus x squared minus x. Yes. We do that subtraction, we'll get 0 here. 0 minus minus x, we get plus x plus 2 when I carry that down. I can only plug in 1 there, and I'm subtracting minus x minus 1. 2 plus 1 is 3. So what this says is that when I divide x squared plus 2 by x minus 1, I get x plus 1, and I have a remainder of 3. And my remainder goes over what I was dividing by, so I've got x plus 1 plus 3 over x minus 1. This part right here that does not have the fraction is my asymptote. Now, if you are using a calculator, you can check these by graphing them, or you can go use GeoGebra and you can graph it there online. But the crux of the matter is, once you break it up using long division, you have one part, which is kind of like a whole part, that gives you the actual asymptote. The other part that I got from the remainder is a part which is diminishing. It's a diminishing part which makes what I have something which is asymptotic instead of a nice straight line. Because if I plug in some small numbers, obviously not x equals 1, then I'm not going to be very close to the line x plus 1. But if I plug in extremely large numbers like 4 million, well, 3 divided by 4 million is going to be a very tiny number. So I'm going to be very close to my so-called asymptotic line. In terms of limits with horizontal asymptotes, what this is saying is that the limit of the remainder, 3 over x minus 1, as x approaches infinity, is 0. That's all we have for our introduction to rational functions for now. Next time, we're going to be looking at the graphs and seeing what the different types of asymptotes are going to look like in terms of the graph.